Hello again. So we resume. So here we saw that the default gateway at R2 is toward the interface 3, but also here at R3 also we have a default gateway. So we have a first entry, second entry. If there's no matching, so we go to the default gateway, which is the interface 0. Here it's a bit weird because usually we don't have a default gateway toward end device, but here just to show you that how to use the default gateway. IP principle number 2, don't use routers inside a LAN. It's very normal. Actually, first of all, let us understand what is a LAN. A LAN stands for local area network. And as we have seen with Epfl network, so all machines that are connected to the same local area network shares the same network prefix. So here the case for B, for B, this machine, and E. I don't know what is the letter of this machine, but anyway, here we have these 3 devices that are connected to the same Wi-Fi. So, and this forms one local area network, and they share the same network prefix. The same thing here, the same for the interface of this router that's connected on the same LAN. So the router in between is between 2 different LANs. So one interface connected to this one, it has the same network prefix as the LAN to which it's connected. On the other side also, I don't show the IP address of this interface, but it must have the same network prefix as the LAN to which it is connected. Now, so B can go directly to E without going to the router because they're directly connected to each other at the MAC layer. So here we have a Wi-Fi. So we have a wireless connection between this machine to the Wi-Fi. Here it is wired. We have a switch in the middle. It is like concentrator. And also, so they can go from one machine to another directly without going through the router if the machine is on the same LAN. Now, the switch actually does not implement a network layer. The switch implements only the MAC layer. The same thing for the Wi-Fi base station. At the Wi-Fi base station, it implements only the MAC layer, the one that we saw at the early beginning. So it does not have a network layer here. This is why the Wi-Fi or the switch are not able to interconnect different local area networks. But the router implements the network layer and is able to interconnect different local area networks. Now, what happens if B wants to go to talk to W? What happens? Actually, let us take a simple case. B wants to talk to E. B will look at the destination address of E, which is this one, 128.178.71.22, and it will compare it against its local forwarding table, because we said every machine connected to the network has to have a forwarding table. Whether it's big or small, it depends on where the machine is placed, but every machine has to have a forwarding table. And usually for end devices, the forwarding table has only 2 entries. The first entry corresponds to the network prefix to which the machine is connected, and the second entry is the default gateway. So B has a packet to send to E. The destination address is 128.178.71. It will compare, it will look at its forwarding table. It will see that this network prefix corresponds to the first entry, which is directly connected. So now B knows that it has not to go through a router because it is directly connected. It will send the packet directly from B to E. But assume now that the same thing for W. W has a packet for the printer, for P. It will compare the packet against its forwarding table. It will find a match, and the match says that this machine is directly connected because it shares the same network prefix with W. So the packet will go directly through the switch to the destination on the same local area network, on the same LAN. But now assume that we have a packet from W to E. What will happen first? So W will look at its local forwarding table, which consists of only 2 entries. The first entry corresponds to the network prefix to which W belongs, and the second entry is the default gateway. So we compare this network prefix with this one, so there's no match. The only option we still have is to go through the router. So the packet is sent to the router, and the router will deliver the packet to the final destination in this LAN. So the principle is that within one LAN, we don't need to go through a router. Between 2 LANs, we have to go through a router because the router is implementing network, the network layer, the third layer, and is able to interconnect 2 different LANs. And again, just to remember that Wi-Fi does not have a network layer. The same thing, the switch here does not have a network layer. Paul, we observe a packet from W to P. So W sends a packet to the printer, and we have an observation point here at 1. Which IP destination address do we see? So I will close the poll in 5 seconds. I will close the poll. So the majority says A. Let us see. So that's the correct answer. This is the correct answer. The majority is right. Actually, let us look at the other options. The IP address of P, actually, it is correct because every packet should have the IP address of the destination. Because here we are using the TCP-IP stack, and to communicate, we have to go through the whole stack, through the whole layers. Whatever the machine is, they connected directly to the same LAN or not. So we have to respect the layered architecture, and the packet has to have carry always the address of the IP address of the destination. If you look at the second option, the IP address of an Ethernet interface of the Ethernet concentrator, this is wrong, simply because this switch does not have a network layer. This is what I said in the previous slide. So it does not have an IP address. It acts only at the MAC layer. There's no destination IP address in the packet since communication is inside the subnet and does not go through a router. This is wrong because we have to go through the layered architecture that I showed at the beginning, and we have to, any packet has to have, to carry the destination IP address and the source IP address.
Sorry, just I have a question. Do we use the private IP address?
Here we might use private IP address here. So it depends where you are. At EPFL, actually, we use public IP address mainly for the wired network, but we might have private IP address. For example, at home, this is very, very typical for home network. It uses private IP addresses.
Okay, thank you.
Most welcome. hop limit TTL. Every IP packet has a field in the IP header called hop limit or TTL. TTL stands for time to live, but it is historical, and actually it is not about time, it's about the maximum number of hops a packet can go through in the network. And the idea behind the hop limit or TTL is to drop packets that are trapped in loops in the network. Actually, what happens at the beginning when a packet is injected in the network, it has some max hop limit or TTL. By default, it is 64. When the packet reaches the first router, the router will check the TTL. If it is equal to 1, it will drop it and it will send an error message to the source of this packet stating that there's an error because the TTL is exceeded. If the TTL or the hop limit, actually why we have two, hop limit and TTL. Hop limit is with IPv6 and TTL is with IPv4, but both are processed the same way. So if the TTL is larger than 1, the router will decrement the TTL and will forward it to the next hop. So this is the TTL hop limit, and this feature of TTL is used as well for another thing, is used to trace the path from one source to a destination. And actually this is what the tool traceroute does. So traceroute is a tool that we have in Linux. It sends a series of packets using UDP with TTL incremented from 1 to 3. So the first UDP packet has TTL equal to 1, the second has TTL equal to 2, and so on. So with the first packet, which has TTL equal to 1, it will be received by the first router. The first router will see, okay, TTL equal to 1, so I have to drop that packet, and I send an error message to the source saying that TTL exceeded. So it will send this error message, and traceroute uses this error message to learn about this router, because with this error message, it is in the end an IP packet, and it has the source IP address. So traceroute is able to learn the IP address of the first router. With the second packet, it has a TTL equal to 2. So it will cross the first router, which will decrement the TTL, and now it's equal to 1. So the packet will receive the second router with TTL equal to 1. The second router will drop the packet and will send an error message to the source. Traceroute will take this error message and will look at the source destination, the source IP address, and will learn about the second router, and so on. Here we have a nice display of the traceroute applied to reach google.com. So here we have tracing the route to google.com. This is the IPv6 address of google.com. So traceroute starts with 30 hops max, and then for every hop it sends three packets with the same TTL, just to have an average of the round trip time between the source and this hop. So here we have the first hop. This is the IP address of the first hop, the first router. Here we have the IP address of the second router. Here we have the IP address of the third router. Here we have the name of the corresponding router, the corresponding IP address. This is something that we will see later. And in the end, we can see that this is the IP address of Google that corresponds to google.com. So the number of hops is 16 hops. To reach google.com, we have to go through this 16 hops, and here we have all the routers that we go through.
Sorry?
Yes?
Why do you have the 3 time values? I do not understand.
Because just to have the average in the end, to know, because sometimes a packet does not need to go through the same path all the time, or maybe it might have some congestion. So just to know what would be the average between the source and this hop.
You do it only once. How can you have 3 values?
Because for every hop, a traceroute sends 3 packets. So it will send 3 packets with TTL equal to 1, and 3 packets with TTL equal to 2, and 3 packets with TTL equal to 3. And for each packet, it will compute the round trip time.
Oh, okay. Thank you.
Most welcome. So with the end-to-end principle, this is the famous principle that I mentioned at the beginning. So the application and transport layer appear only in the two endpoints of the communication. In the middle, we have at most only the network layer. Why we have this? Because it makes our life much easier, mainly the life of programmers that want to create new applications. So assume that we need the application to be deployed at every hop in the network, and assume that you want to create a new application. What will happen? So you create your application, you are happy, you deploy it on you deploy it on your local machine, you deploy it on the the other endpoint, the destination, but nothing will happen because you need to deploy it at every node in the network, in the internet, so that you can communicate from your machine to the destination. And it's very bad. That's why we have this end-to-end principle. The application appears only at the endpoints between the source and the destination. So you develop your application, you deploy it in your machine, you deploy it on the other endpoint, and that's it. And you can now use the communication service that is provided by the transport layer and that's provided by the network layer. And also another reason is that if you deploy application layer at every node in the system, this means that you are using store and forward, and as we have seen before, it's not very good for the performance. But we have some violation of this end-to-end principle for good reasons. Now, with the mail service, we have an email that goes from the source, the mail client, to the mail server. Then from this mail server to the destination mail server, and then from this mail server to the mail client of the destination. These servers in the middle applies store and forward. And these are, we have the application, the mail server that's running here. It is not only the network layer, we have a transport layer, we have application layer, and we have as well store and forward, and at these two points. But in between A and X, it's packet switching. Between X and Y, it is packet switching, and between Y and B, it is packet switching. So store and forward is applied only at Y and X. So if you would like to apply the end-to-end principle here, how can we apply it? So the end-to-end says that A has to communicate directly with B without going through intermediate application nodes. So this means that A sends the email to B and directly. Assume that B is not connected, the example that I gave previously with WhatsApp and email. So the message can go nowhere. So violating the end-to-end principle allows us to have more mobility in the application.
But WhatsApp says that they are end-to-end encrypted. Is it related to this or not?
Encrypted is different. So the WhatsApp server can keep the message, but it's still encrypted. So encryption does not mean it's encrypted at the network layer. It's encrypted at the application layer, but it simply does not apply. It does not decrypt your message, but it can keep the whole message at the application server at the server in the middle. Did I answer your question?
Yeah, thank you.
Most welcome. Okay, so this one example of violating the end-to-end principle for good reason. Now we have another example of violating the end-to-end principle again for good reasons. Actually, it is the network address translation boxes. If the IPv4 is still surviving till now, it is thanks to the NATs. So the NATs actually separate the intranet from the internet. The intranet, again, is the network that we can have inside a company, a university, maybe at home. So it is a set of machines that need to communicate internally without going to the internet. This is the intranet. And the internet is the public network that we know. And the NAT separates its place just in between the intranet and the internet. And with within the intranet, we can use the private IP addresses, but these private IP addresses cannot traverse, cannot appear in the internet, otherwise the packet is dropped. And this private intranet, these private IP addresses are unique within the intranet, but they're not unique worldwide. So if we have this intranet for this company, so in another company, we can use the same IP addresses in another company. And this IP addresses are used not only tens of times, hundreds of times, they are used hundreds of thousands of times within different intranets. But the public IP address should be unique worldwide. So in this example, we have this the intranet. All of these are private IP addresses. And here we have a public IP address. And one public IP address for the net that is exposed to the internet for the tens or hundreds or hundreds of thousands private IP addresses that are hidden behind the net. So here we can use many, not as many as you want. We have some other space, but it's huge, it is large. So it should be enough for any intranet. But all these private addresses are hidden behind one public IP address, and this is how we can still use the IPv4 for the internet. What happens actually when this machine needs to communicate with the internet? The net will simply replace the private IP address by its own public IP address, and when the server replies with this public IP address, so the net will replace its public IP address by the private IP address of the machine that is behind this communication. How the net is able to map, to preserve, to maintain a mapping between the packet that arrives at this public IP address and the destination that are behind, because this packet can be destined to this machine or to this machine. To do that, the net maintain a net table. In this net table, on one side, the left side, let us say the intranet side, we have several entries. At each entry, we have the private IP address of the machine, and also we have a number. This number is called a port number. Actually, the port number is a number that indicates the application that's above the transport layer at this machine, because the transport layer can serve at the same time many applications. So on your computer, you might be using Zoom, web browsing, YouTube, listening to music. You might use also WhatsApp if you want. So you might have many applications running at the same time and requesting the communication service or communication service from the transport layer. So the transport layer distinguishes between these applications by giving a port number to these applications. So for example, let's just assume you are using YouTube. So the port number for YouTube is 1029. If you are using a same time web browser, the port number for the web browser is 80. So when the transport layer receives a packet with a port number equal to 80, it knows that this packet corresponds to your browser and will deliver the packet to your browser. Now the net will receive a packet from this machine. Okay, it will create a new entry for it in the net table if the packet is the first time it is received for this application, and then also it will note the port number that indicates the application that is above the transport layer. And the other side, it will replace the private IP address of this machine by its own public IP address, and then it will create a random port number, which it will keep it for the whole communication, for the whole connection that corresponds to this entry. And then it will replace these two numbers inside the packets and will forward the packet to the internet. So in the way back, from the server to this machine. So this is the packet that we receive. The destination IP address is the public IP address. It's normal. The port number is this one. This one corresponds to this entry, and this means that these two numbers should be replaced by the first line on the left side of the table. And this is how the packet will reach the origin, the other point of the communication channel. Another packet arrives at the NAT with a public IP address, but with a different port number. We look at the NAT table, we see that this entry corresponds to this entry. We replace these two numbers by what we find on the left side of the NAT table, and then the packet is forwarded to the right machine. Application layer gateway, it is another way to violate the end-to-end principle, again for good reasons. Here I am showing an example of a web proxy. So at your browser, you want to reach some web server. In the middle, at Epfl, we deploy a web proxy. This web proxy will intercept your request. It will process it, maybe deny it, maybe just authorize it, and then it will forward it to the final destination, to the web server. And as we can see here, in between, we have packet switching. Here we have store and forward. Here again, packet switching, and here for sure we receive the whole message to process it. And again, so here we have at the source, we have the TCP-IP, we have, okay, this is the TCP-IP stack. Okay, so yeah, so this is an example, another example of violating the end-to-end principle. Now, why we would use a web proxy? Assume that we have a user here at Epfl. It requests an image from a web server, bb.an. The request is intercepted by the web proxy of Epfl. So the Epfl web proxy will forward the request to the web server. The web server will send the requested data to the web proxy. And then the web proxy at Epfl, it will do two things. The first thing, it will forward the data to the user that requested this data, and at the same time, it will keep the image in its cache with some expiry date. So if another user requests the same data, so the web proxy will be able to reply with the image from its cache. So in that way, it reduces the traffic that towards the internet. So also this means that we reduce the congestion we might have between Epfl and the internet. And we know that the connection here, we pay for it, and we need, if you can save it or reduce the consumption on it, or it would be better for Epfl. Now, if a third user requests the same image, but the image is expired, the web proxy at Epfl will request again the image from the web server. Now, what would be good reasons for desiring an application layer gateway? So what would be good reasons for violating the end-to-end principle of internet, of TCP-IP networking? So the first one good reason is mobility. This is what we saw with the mail server, with WhatsApp. The second reason is security. So when we intercept requests for other servers, we can apply some logic, some content filtering, so we can deny access or authorize access. So just also this is what we'll see in the next slide, to minimize the exposure of machines to the internet. So we have for interworking, because IPv6 and IPv4 are not compatible. If you put IPv6 machines to communicate, and you want that machine to communicate with an IPv6 machine, they cannot. So to make it possible, we need to put something in the middle that is able to communicate with both sides. And this one solution could be the application layer gateway. And in the end, for performance, especially with TCP, because it has some deficiencies with lossy connections or with connections that have large delay. So in this case, we split the network into two parts just to counter TCP issues with such connections. Now, another use of the application layer gateways is the firewall, is the security, for security reasons. So here we have the intranet. Here we have the intranet. In the middle, we put the firewall, the application layer gateways that will apply some filtering on the traffic in both sides. And also, in that way, the only machine that's exposed to the internet will be this firewall. So for the admin, for the network administrator, or for the admin, the sysadmin, it's much easier to control what's happening on this machine, to monitor everything than monitoring all the machines in the intranet. So using this firewall is to apply filtering and also to reduce the exposure of the machines that are in the intranet. Another way to apply this to reduce the exposure for for large networks like EPFL. So for EPFL, it would be very hard to expose only one machine. We might need several firewalls, several machines, several proxies. That's why we create what we call demilitarized zone. So the only exposed network to the internet will be this zone, this DMZ. Within this DMZ, we find all the proxies that we have, and also we add another layer of protection through these two routers that will apply filtering here and other filtering here. Now, names. So far, we played a lot with numbers, but numbers is very hard to remember. So with IPv4, we can survive to remember few numbers, but forget it with IPv6. It's very hard to know the numbers. Assume that you want to talk to epfl.ch, you need to know by heart the IPv6 of EPFL or of Google or whatever server you need. So to solve this problem, to make this address human readable, we use names. We gave names that are synonyms for IPv4 or IPv6 address. For example, when you put epfl.ch on the browser, this name will be translated by the application behind to an IP address. But for you don't need to remember to know this IP address. All what you need to remember is the epfl.ch, and this will be automatically translated later to an IP address. The same thing for SMTP sunrise.ch. So also this is a name that you can remember, but this one will be translated to an IP address behind. And now the names also, they're structured. So we go from more specific on the left to less specific on the right. So here on the right, we have two letters. This means that it's the country. CH means Switzerland. And on the left, we have SMTP. This indicates the service that we are addressing within Sunrise company. Here we have the country. Here we have the company. And here we have the service inside this company. And here we see that we have two letters. It means that it's a country. Here we have this to everything related to commerce. Here we have aero. This means that to everything related to aeronautic sector. And we can imagine to have any kind of domain name here. And you can create your own domain name and buy it and book it if you want. Now, how this mapping names IP address is maintained. Actually, it's maintained by what we call DNS. DNS stands for name server, domain name server. So these servers maintain the mapping between names and IP addresses. And the mapping is not only one-to-one. We might have one-to-many and many-to-one. Now assume that we have Alice is standing, wants to have some data from the web server ssc.epfl.ch. The first thing it does is it will put the name in the web browser and click. So here we have the click. That's all what she does. Behind this click, what happens is that the name SSC EPFL needs to be resolved. So there's a request that flies from Alice machine to the domain name server of EPFL. So this domain server will resolve the IP address and replies to Alice. The domain name server does not need to ask for the IP address of Alice because it's already in the request, in the source IP address of this request. So it will reply to the same IP address with the IP address of the web server requested. That now, once Alice has this IP address, is able to communicate with the web server. Now we have a packet that flies that goes to the web server, having the IP address of this web server as the destination IP address, and within the IP packet, within IP packets, we don't use names. So we use only IP addresses. So the IP address, the name does not appear at all in the header of the IP address, but it might appear in the payload that is carried in the IP packet. So at the network layer, we don't use at all the name, we use only IP address. But again, the name might appear at the application level in the data that are sent by the application. And now the web server is able to reply to Alice because it knows through the request it receives the IP address of Alice. The MAC layer, link layer, actually it's called sometimes link layer or MAC layer, they're both the same. So that interconnects a small number of devices without any configuration. We'll see why a bit later. Okay, so this is a LAN devices connected to a Wi-Fi base station with the router that's as well connected to this Wi-Fi base station. All this belongs to the same local area network and they're connected through MAC. Remember that the Wi-Fi base station does not implement a network layer. The same thing here, we have all these machines connected together through this switch. So they belong to the same local area network and they are connected at the MAC layer. Again, the switch does not implement a network layer. Actually, okay, I will go back to the MAC layer here. Actually, the MAC layer, MAC stands for medium access control. So the role of the MAC layer is to control the access to the same shared medium. It appears mainly with the Wi-Fi. So with the Wi-Fi, we have one shared medium. So if this machine sends something on the Wi-Fi, this frame is received, is heard, can be heard by other machines because it is the same medium. It's shared among the different devices connected to this Wi-Fi. And this shared medium might have collisions. So these two machines might start transmitting at the same time. So this creates collisions. And one of the objectives of the goal of the MAC layer is to arbitrate among these devices that are accessing the same medium. Here with the switch, we don't have this collision issue, but it was historical. This is because historically, all these machines were connected to the same line. So it's exactly the shared medium like the Wi-Fi here, and it was the same collision domain. So if two machines start sending at the same time, so they will have collision. And the one goal of the MAC layer was to arbitrate among these different machines. Now at the MAC layer, we have also MAC addresses. The MAC addresses are they are hard-coded on the interface. So this is not a configuration that we do the interface like with IP. It is hard-coded when we buy a network interface, an adapter. So it comes with its MAC address. So it is a 48 bits. It is not structured. The only thing that we might have inside this MAC address is a few bits that indicate the manufacturer of the MAC layer, but there's no structure in this MAC address. So the only thing we can know is that there's few bits that indicate the manufacturer of the corresponding card, but there's nothing that there's no structure, because if you buy a machine, if you buy a laptop and you put it in some network at Epfl, for example, it will be configured automatically or manually according to where the machine is placed. So the IP address that you will get corresponds to the IP address of the local area network where you place your machine. If you take your machine and you plug it at home, you'll get another IP address according to the LAN where the machine is plugged. But in both cases, you have the same MAC address that will not change. So the MAC address will not give any information to which network you are connected. And here, so why we need the MAC address? Because let us consider this example. In this example, this machine A is sending a data to the router. It's a shared medium, it's Wi-Fi. All these machines are able to hear the frame, but they will keep the frame only if the destination MAC address corresponds to their MAC address. So this machine, here we have the MAC address of the router. So this machine will look at the destination MAC address. It's not does not correspond to its MAC address. It will ignore the packet. The same thing for the smartphone. It will ignore the packet or the frame. The router will look at the MAC address. It corresponds to its MAC address. It will keep it. It will deliver the frame or the packet to the network layer to process it.
Sorry?
Yes?
Why not use the IP address also instead of MAC address?
The IP address is used at the IP layer, at the network layer, not at the MAC layer. So the objective of the MAC layer is to ensure the communication between this machine and the router, but the network layer, the IP is used to interconnect this network with other networks. So and this is historic actually. Anyway, we need the TCP-IP stack that we have. We have the MAC layer, and for that we need and the communication here within one LAN is based on the MAC layer.
I'm sorry, but I don't understand too, because one of the polls you did, you asked us inside an intranet
yes,
what was sent, and you said it was an IP address, and now you're saying that
okay,
it is a MAC address.
Okay, you're right. Actually, the packet, the frame that's sent by this machine has an IP address, but the IP address appears at the network layer. So this machine, this packet, has one header for MAC layer, and another header that does not appear here is the IP header. So the IP address will appear in the IP header in this part here, that carries some information regarding the IP layer, the network layer. But here at the MAC layer, at the MAC header, we have only the MAC address. So this means that in this packet, we must have the IP address. A destination IP address might be the destination IP address of this router or another another machine that behind this router. So we have an IP address here, but the MAC address should be the MAC address of the next destination. Okay, I will give you an example, another example. Assume that you want to communicate from this machine to another machine on another LAN. So the destination IP address should correspond to the IP address of the machine that is on the other LAN. But you know that this machine knows that the destination is on another LAN, so it has to send a packet to the router, which will provide the interconnection between these two LANs. So the next hop at the MAC layer of this packet is the router. So this machine has to set the destination MAC address to be the one of the router to be able to receive it here, and then it will forward the packet to the network layer. It will see that at the network layer that the IP address does not correspond to its IP address, and it has to forward it to another machine, and then it will forward the packet to the final destination. But here, the destination of this packet here is this router. This is why we use the MAC address of this router. Is it
okay
clear?
Yeah, I think I understand.
Okay, and we'll see this in more details later. But now for the MAC address, the destination MAC address indicates the machine that will receive the frame or the packet on the same LAN. This machine does not need necessarily to be the final destination, but the IP address indicates, the destination IP address indicates the address of the final destination that might be far away from the local network where we are right now. Okay, we'll see this more in details in the coming slides. I think now it's time to break, and we'll resume in 15 minutes.